Most wearable devices we see today were designed for adults. Smartwatches, fitness trackers, and research-grade sensors can provide useful information, but when we talk about young children, there is a major problem. Children are not just small adults. Their movement patterns are different. Their bodies are still growing. They move in short bursts. They stop suddenly. They run, sit, jump, and play in ways that are hard to measure with devices made for adult routines. Another issue is that many commercial wearables use proprietary algorithms. In simple terms, the data goes into a black box, and researchers do not always know exactly how the final result was calculated. That creates a challenge for science. If we want to measure physical activity and energy expenditure in children with more accuracy, we need tools that are designed specifically for them. In today's video, we are going to look at a scientific article that presents the initial validation of Patch, an open source device created to estimate oxygen consumption in children aged 3 to 8 years. And if you are interested in exercise science, physical activity, public health, and scientific research explained in a clear way, subscribe to the channel and follow the next videos. Now let's understand what the patch is and why this device was developed. So let's look at what this device is and why the researchers developed it. ATCH stands for Platform for Accurate Tracking of Children's Health. It is an open source chest-mounted device created to measure two important signals: heart rate and body movement. Heart rate gives us information about how the body is responding physiologically. Acceleration gives us information about movement. When we combine these two signals, we get a stronger estimate of the child's activity than we would get from movement alone or heart rate alone. One important detail is that the patch was designed with children in mind. It has no screen, which helps reduce distraction. It is placed on the chest instead of the wrist, and it uses skin-friendly adhesive to improve comfort and wearability. Another major strength is that the patch is open source. That means the hardware documentation and the software code are publicly available. For researchers, this is important because it improves transparency, reproducibility, and the possibility of improving the device over time. But here's the key point. In this study, the researchers were not directly proving total energy burned in every real-life situation. They were testing whether patch data could accurately estimate oxygen consumption, or VO2, which is a physiological measure closely related to energy expenditure. Now that we understand what patch is, let's see how the researchers tested it. The study included 52 children between 3 and 8 years old. The average age was 6.4 years, and the sample included both boys and girls. Each child completed a laboratory protocol lasting about 45 minutes. The activities followed a sequence from low intensity to higher intensity. First, the children lay down, then they sat, then they stood. After that, they walked. Finally, they ran. During the protocol, the patch was placed on the child's chest and collected heart rate and acceleration data. At the same time, the researchers used the Cosmed K5, a portable metabolic system, to measure oxygen consumption through indirect calorimetry. This is important because the Cosmed K5 served as the criterion measure. In other words, it was the reference method used to compare the patch estimates. So the main question was simple. Can a small open source device placed on the chest estimate children's oxygen consumption with good accuracy? To answer that question, the researchers tested 3 different prediction models. The patch collects raw signals, but raw heart rate and movement data do not automatically tell us oxygen consumption. So the researchers needed mathematical models to translate those signals into VO2 estimates. They tested 3 approaches. The first was CSTS, or cross-sectional time series modeling. This model is useful because it considers patterns over time and repeated measurements from the same child. The second was GAMM, or generalized additive mixed modeling. This approach is flexible and can capture nonlinear relationships in the data. The third was random forest, a machine learning approach that uses multiple decision trees to identify complex patterns. All 3 models used information from heart rate, acceleration, and child-level characteristics such as age, height, weight, and biological sex. The goal was not just to create a complex model. The real goal was to find a model that could estimate oxygen consumption accurately while still being useful for future research. Now let's look at the results, because this is where the study becomes especially interesting. The results were promising. The CSTS and GAMM models performed best. Both explained about 86% of the variation in children's oxygen consumption. That wording is important. It does not mean the device measured 86% of oxygen consumption. It means that the models were able to explain 86% of the variability in VO2 compared with the criterion measure. The random forest model also performed well, but slightly lower, explaining about 81% of the variation. The average absolute percent error was around 10% for CSTS and GAMM and about 13% for random forest. So in this initial laboratory validation, the patch produced estimates that were fairly close to the Cosmed K5. The figure on this slide helps show the comparison between the models. CSTS and GAMM had lower error and slightly stronger performance, while random forest was still useful, but not the best model in this sample. One important detail is that all models showed a small tendency to overestimate VO2 at higher activity intensities. So when the children were running or working harder, the patch-based estimates tended to be slightly higher than the Cosmed K5 values. This does not invalidate the device. Instead, it shows where future improvements are needed. So why is this device important, especially for researchers and professionals working with children? The patch stands out for several reasons. First, it is open source. That means researchers can inspect the device design, examine the code, and adapt the system for future studies. This is very different from many commercial wearables, where the algorithms are closed and can change after software updates. Second, the patch is designed for children. The chest placement may help reduce some movement artifacts that happen with wrist-worn devices, especially because children move their arms a lot during play. Third, it is modular. This means that future versions can potentially include new sensors or improved components. And fourth, it may be more accessible for research. Research-grade devices can be expensive, fragile, or difficult to maintain in field settings. An open-source platform creates the possibility of a more flexible and transparent tool, but it is important to stay balanced. The patch is not yet a finished solution for all real-world monitoring. This study shows strong initial evidence in a laboratory setting. That is a very important first step, but it is still the beginning of the validation process. And that brings us to the limitations of the study. This study has important limitations. The first limitation is the setting. The test was conducted in a laboratory, not in a real-world environment. Children followed structured activities with fixed times, lying down, sitting, standing, walking, and running. But real childhood movement is not that organized. Children move in sudden bursts. They stop, they change direction, they play games, they climb, jump, and interact with other children. That makes real-life activity much harder to measure. A second limitation is the sample size. 52 children is a useful starting point, but larger and more diverse samples are needed before the algorithms can be considered ready for broad use. A third limitation is that the study did not test long-term wear in daily life. We still need to know how well children tolerate the device over multiple days during school, play, sleep, heat, sweat, and normal family routines. Also, the study used oxygen consumption as the outcome. That is a strong physiological indicator, but it is not the same thing as directly measuring every aspect of total energy expenditure in real life. So the message here is not the problem is solved. The message is this device shows promise and it deserves the next phase of testing. So what does this mean for the future of pediatric wearables? The patch represents a promising step forward for pediatric physical activity research. It helps bridge an important gap between expensive research-grade devices and commercial wearables that often hide their data processing. The authors describe this as an early phase of validation. In this phase, the patch performed well in a controlled laboratory protocol. The next step is to test it in more realistic conditions. That means semi-structured activities first and then free living studies where children use the device during normal daily life. That final step is essential because the real test is not only whether the patch works when a child is walking or running in a lab. The real test is whether it works when children are being children. Running, jumping, stopping, playing, sweating, laughing, and moving unpredictably. If future studies confirm these results, the patch could become a valuable tool for researchers studying physical activity, oxygen consumption, and health in young children. And because it is open source, it may also help make pediatric wearable research more transparent, accessible, and collaborative. So the main takeaway from this article is this: to measure children well, we need tools designed for children. The patch is not the final answer yet, but it is a strong and promising step in that direction. If you found this article interesting, leave your comment below. What do you think about open source wearable technology for children's health research? Also, like this video and subscribe to the channel if you want more scientific articles explained in a simple and practical way. Science becomes more useful when we can translate complex data into tools that help us understand real life. See you in the next video.